Yeah, good morning. This is Dr. Vijaya Babu. So we have been discussing about the concepts of network analysis from the past so many videos, right? So yeah, today we are going ahead for the new lecture. So that is about the Kirchoff's current law. If you really remember the last lecture, what we have done, so we have done with the Kirchoff's voltage law (KVL), and I have solved some of the problems in the KVL. Okay, so in today's discussion, we will try to go ahead with the concepts of KCL, right? So usually I can say one important thing is that the KVL is the voltage phenomena, whereas the KCL is the current phenomena, right? So the KCL, Kirchhoff's current law, is associated with the currents at the node, okay, whereas the KVL that you are using is a phenomena related to the voltages in a loop. So this is the major difference between KVL and KCL. KVL is voltage in a loop. KCL is current at the node. So I'll try to start with the concept of KCL here. So as I'm saying that it is at a node concept. So at a node, there are two types of nodes. Okay. So one is a simple node, another is the principal node. What is meant by the simple node? Right. So simple node, it is a junction of two branches. The node, we can call it as a simple node if it is a junction of two branches, something like this. I will try to show you with a simple example. So there is a resistor something here and there is a capacitor something here. Okay, then the node A, usually call it as a simple node. Node A, we can call it as a simple node, right? Yeah, going ahead. What is meant by this principal node? So it is a junction of, it's a junction point of three or more branches, compulsory. It is a junction of three or more branches. So that means I will try to tell you, draw here one simple example of a principal node. So let us assume it is 4 ohm, it is 4 ohm, and it is 10 microfarad. Let us assume, and here the point, the node which is joining all of them, here we can call this as node B. Let, for example, now in this analogy I can say node A is, I can call it as simple, whereas node B you can call it as principal node. Okay, so this is the basic information about two different types of nodes that appear in the network analysis, right? So immediately you can ask me one important question, that whether KCL is possible to apply at the simple node as well as the principal node, right? So grantedly you can apply the KCL at any node. You can apply KCL at the simple node, or else you can apply the KCL at the principal node, right? Okay, so usually how can you write the definition of this KCL? That is, it is nothing but algebraic sum of currents entering a node is 0. Algebraic sum of currents entering a node is equal to 0. What was KVL then? KVL was algebraic sum of voltages in a loop is 0. This is algebraic sum of currents entering a node is 0. Okay, to avoid confusions, usually I don't want to use this complex but fight statement. Rather than that, I want to make a little bit simple. That is, I will try to understand the same statement in a different way. That is, sum of entering currents at a node is exactly equal to sum of currents .  . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . at a node. So this is straightforward simple definition of this KCL. So let us consider there are three branches, something like this, and the currents are. So if you want to apply the KCL at this point P, KCL at this point P, sum of entering currents. So whenever you are applying the KCL, what you have to do is you have to stand exactly on the node. To apply KVL, you have to walk along the loop, as I said earlier. Here you have to stand, you should be at rest at the node. You stand at the node and think of which are the currents coming in and which are the currents going out. So that means simply I can say I1 plus I2 are the currents that are entering the point P. You are standing at the point P is exactly equal to the current I3 that is leaving. Right. So one more example. So there are four resistors which are tied together at a principal node Q, something like this. So which are having values R1, R2, R3, R4, and the current here it is I1, current here it is I2, current here it is I3, current here it is I4. So apply KCL at node Q. It is very simple. All the currents entering is equal to all the currents leaving. So all the currents entering usually, what are the currents entering? I1 plus I2 plus I3 plus I4. Here unfortunately all the currents are entering, right? Is equal to what is the number of currents that are leaving? There are no currents leaving. So that is why it is exactly equal to 0. Okay, right. So now one more simple example on this KCL. A inductor connected here, a capacitor connected here, a resistor connected here, and you have connected a diode as well, something like this. Okay, so this is of 2 Henry, 4 microfarad, so 2 ohms, and it is of a diode, something like this. Then if I try to mark the currents in these branches, so I'll try to mark the current something like this. This is I1, so this is I2, so this is I3, and it is I4. Okay, then is it possible to apply KCL in this particular point? Okay, so this is very important, right? Because here there are non-linear device, something is connected, diode is connected here. Whereas the resistor, inductor, capacitor are linear components. Coming to this diode is a non-linear component. Then is it possible to apply the KCL exactly at this node Q? Okay, so grantedly yes. KCL is a node phenomena. It is not the phenomena that what you are going to connect in the branch. Okay, it is always the current entering the node and the current leaving the node. So I can write in this case also I can grantedly write currents entering the node I1 plus I2 is equal to the currents that are leaving the node I3 plus I4. Okay, so in this way I1 plus I2 equal to I3 plus I4, even I can apply the KCL in such cases also, right? Okay, so having this in mind, so we'll try to go ahead in solving the problems of KCL. So two basic problems of KCL I'll try to solve in this video lecture, right? So the question here it is saying that he is asking to calculate the value of Vx. So there are a lot methods in network analysis where you can go ahead in applying or solving the electrical circuit problems or network analysis problems. Okay, so this problem is something related to the KCL because the KCL will make this problem solution very simple. So let us consider this is a node. To solve this problem, let us consider this is the node something at P. Okay, so now try to indicate, or let us assume this current is something I, and try to write down the currents around that node P. That means this current is 4 amperes. Okay, and this current is 4 amperes. Now apply KCL at node P. So we apply KCL at node P. 4 plus 4 are entering is equal to leaving current I. So from this I am getting it as I is equal to 8 amperes. Okay, so once you get the value of I, which is equal to 8 amperes, then it is very easy to calculate the voltage drop in that resistor, 2 ohm resistor, right? So that means voltage drop in the 2 ohm resistor is current I is entering the positive terminal of Vx, so no issues directly. It is something 2 into the current I. Okay, so that means 2 into 8, so this is exactly equal to 16 volts. So with a simple KCL, we can solve this problem and to calculate the value of Vx. Okay. Similarly, we will try to go ahead for the next problem. So that is the next problem is the calculation of Vx plus Vy. Okay. So to solve this problem, many times I said whenever some unknown things or unknown parameters are given in the circuit, to go ahead compulsory you try to first step you try to erase the unknowns and take the circuit in your control. Okay, so you try to erase the unknowns and you try to take the circuit in your control. So that means how to erase the unknowns. So I'll try to plot here, try to understand. So this is a 2 ampere source which was already given in the circuit. Okay, and it is a 2 ohms resistor and it is a 3 amperes current source that is given, and this is 4 ohms and this is 2 ohms, something like this. Okay, so from this, I think once again, let us consider this node as something P, and we will try to apply this current, take it as I1 that is 2 amperes, and this current you take it as I2 that is 3 amperes, and this current coming out of it is try to consider it as I. So now it is very simple. So apply KCL at node P. Okay, so if you try to apply KCL at node P, then 2 plus 3 is equal to I. So I is equal to 5 amperes. Okay, so that means I is equal to 5 amperes. So always the current I enters the positive terminal. Let us assume this voltage is VA and this voltage is VB. Okay, as this is in my control now, I indicate my own voltages to calculate the voltages. Okay, so I indicated VA and VB and I have chosen that the current is entering the positive terminal of the voltage notation. Okay, so here the current entering the positive terminal of the voltage notation. Here also the current is entering the positive terminal of the voltage notation. That means current is entering the plus VA. Similarly, the current is entering the plus VB. So then it is very easy for me to apply Ohm's law now. That means from Ohm's law, VA is equal to I into resistance value. That is equal to I is something 5 into 4. So how much it is? 20 volts. Similarly, the value of VB is equal to current is entering the positive terminal now that I have assumed I into the resistance value 2. So this is something like 5 into 2, so which is equal to 10 volts. Okay, now finally the value of, you need to check the value of Vx and Vy, right? So unfortunately the Vx and Va both are in phase. On observation, I can easily write, right, the value of Vx is exactly equal to Va, which is equal to 20 volts, right? But coming to Vb in the question, here I have mentioned Vb as something like this, but Vy is something in the with the opposite polarity it is mentioned, right? So that means the value of Vy I can read as minus Vb. Okay, and minus VB, already VB value I got it, right? So that means you can write it as minus 10 volts. So from this logic, simply the value of the question is Vx plus Vy. As I got the value of Vx and Vy, it is very simple to substitute in that. So that means 20 minus 10. So and this value is given as directly 10 volts. So the students try to prefer this type of method. So try to erase the unknowns and take the circuit in your control and try to give your own notations for the voltages and then apply Ohm's law to calculate them. And finally, you try to compare, okay, with the original unknowns with the unknowns what you have assumed. Then you will be getting the right answer. There is a less chance of making the mistake in this type of procedure. If you try directly go with minus Vy, then compulsory there is a possibility of making the mistake. So I think this type of procedure will be very clear and you can go ahead. Okay, so thank you for giving this opportunity to discuss the concepts of KCL and the problems on the KCL. Okay, so we will try to go ahead in the next lecture with a new concept. Okay, thank you for giving this opportunity. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.